and they lived upriver, right next to me on the Charles River. So please use this link that I'm sending to the chat to learn more about. Please use this link to learn more about sort of the indigenous lands from which you are joining us. And through the acknowledgements of past farms, we can move towards more equitable and humane. So on behalf of all the students and postdocs on the organizing committee of this seminar series, I'm excited to welcome you to today's seminar. The organizing committee represents a consortium of colleges and universities, including Dartmouth, Gallaudet, UPenn, Yale, MIT, Princeton, Harvard, and Columbia. And we are a consortium that is committed to highlighting advances in cognitive neuroscience research. We acknowledge the privilege of these institutions, and we wish to make science that is discussed here available and accessible. So with the consent of our speakers, we plan to make these talks publicly available on our website, and our seminars are open to anyone who is interested. So a quick note to those of you who are new, after the talk is over, we're going to move to another Zoom room for an informal Q&A. I'm going to paste the link to that Zoom room in the chat as well. And it's going to be a space for trainees in particular to ask questions to the seminar speaker, either related to or beyond the talk. Which brings us to today's speaker, which I'm very excited to introduce. So today we're very fortunate to have with us Dr. Vta Mogghadam. Dr. Mogghadam received her PhD in biochemistry from University of Kansas, working with Ralph Adams. And then she did her postdoc at Yale with Benjamin Bunny. So I read online that during this postdoc, she published 6 first author papers in 3 years, which sounds amazing to me. And then after that, she quickly joined the faculty before moving up to full professor. And she joined the faculty back in 1990. She moved to University of Pittsburgh in 2003, and then in 2017, she joined Oregon Health and Science University, where she's currently the Ruth Matarazzo Professor. So I first met Vta, I don't know if she remembers this, during a scientific advisory council for one of the grants that my lab was on. So I happen to know her as one of the top experts in the world on the anesthetic drug ketamine, which she has written a book on. But her expertise extends to conditions spanning both neurodiversity and mental illness, including schizophrenia, ADHD, anxiety, addiction, and others. As you'll see, Dr. Mogghadam's research is highly translational, which I've always appreciated, but I think you may also recognize that Dr. Mogghadam has designed a research program that is able to really traverse all levels of analysis, from biochemistry to systems to cognitive, and then to the clinical level. Dr. Mogghadam's research has earned her multiple honors and awards, including the Paul Johnson Award for excellence in schizophrenia research, the Daniel Effon Award for excellence in neuropsychopharmacology, another award in 2014 from the International College of Neuropsychopharmacology, and the Merit Award from the NIMH. And this is just to name a few. It's not only sort of Dr. Mogghadam's rigorous and innovative science that makes her a pioneer. She's also a thought leader on gender and racial diversity and equity in neuroscience. And today she's spotlighting the ALBA network, which performs global advocacy work related to these issues in neuroscience. Without further ado, please join me in welcoming Dr. Vta Mogghadam, and she'll be presenting her talk, Translation of Anxiety into Actions. Yeah, all right, take it away.
Thank you so much, David. And that was a wonderful and humbling introduction. I had all those papers as a postdoc because we actually published shorter papers. We didn't have, at the time, it wasn't routine to have papers with 20 figures, each of them, multiple panels. So don't feel bad that as a postdoc, any of you, that you don't have as many papers. It's truly an honor and a pleasure to be here and tell you a little bit about some of the newer stuff that's going on in the lab. I won't be talking about ketamine, but if you're interested in ketamine, I did actually write a book. David is correct. It's a simple and short book and should be an easy read if you're interested in understanding about learning about the history of ketamine. But today I'm going to talk mostly about some of the recent work we've done related to anxiety. And I'm sorry that I am sort of, I can't look in the camera because I'm using two computers because I have some laptop issues. I have to go grab the second laptop, so I have my iPad on this side and an older laptop on the other side. Okay, so if I stop my video, can you see this slide, right? Okay, good. That way I can get closer to the iPad so you can hear me better. So let's switch to what I'm going to talk about today, which is thinking about how we can measure anxiety better and how the brain actually encodes anxiety. Before I tell you about the data and experimental design, two acknowledgements. One, I am grateful for mouse. You see it now? Great, perfect. I'm grateful to the funding agencies, especially the American taxpayers and NIH, for funding our research for many, many years. And also, I'm grateful to the trainees that really helped with this project. This particular project, more than anything else in the lab, has really been a product of a number of really clever trainees that have helped me think about how to design what we were actually thinking about in terms of the questions that I will be telling you. These trainees include John Jewel Park, who was a graduate student in the lab when I was at the University of Pittsburgh. The same with Sweta Lohani, also a graduate student. She's currently in Jess Cardin's lab at Yale. Nick Simon, who's now a tenured associate professor at the University of Memphis. And David Jacobs, who's a graduate student who just defended at OHSU in my lab. So, those of us who are interested in translational models relevant to psychiatric illnesses know that animal models of complex brain disorders have become or are becoming somewhat obsolete. So, in maybe a couple of decades ago, we could claim to have a model of schizophrenia, mood disorder, PTSD, etc. But now we know that we really don't have good animal models for these, or you cannot actually have perfect animal models of schizophrenia. But what we are focusing on as a field is to more model specific symptoms or focus on studying how we could actually prevent the onset of these illnesses. I do have about half of the lab actually working on adolescent models, which could be focused on preventive measures. But for today, I'm going to talk about one of the most prevalent symptoms, which is anxiety. Now, why anxiety? Anxiety is a developmental symptom of many brain disorders, including mood disorders, autism, schizophrenia, and addiction. Anxiety is also a common symptom of most neurodegenerative illnesses, including Parkinson's and Alzheimer's. And most clinicians know that by effectively treating anxiety, outcome of nearly all brain illnesses could improve. Now, if you are actually measuring anxiety in the lab, you could argue that there are some good animal models. But we weren't interested in really using those models because the questions that we had, and in my lab, we always try and start with the question, or at least I really force people to think about the question that they want to ask before we start doing experiments. How does your brain deal with anxiety? Now, what do I mean by that? Well, when we look at the animal models that we have to assess anxiety, those of you who have done some behavioral neuroscience know that you could do some fear conditioning studies, or a common behavioral task is the so-called elevated plus maze task, where animals are allowed to be in an area that is not anxiety-provoking, like a closed arm, or be in an open area which could be potentially anxiety-provoking. So if the animal is here, it's feeling really anxious because it's potentially fearing falling outside the maze. So those, you could argue, can be modeled this way, or this is what we are modeling in the case of humans. And this is not what we really wanted to model. What we wanted to model was real-life anxiety in the context of goal-directed engagement, goal-directed behavior engagement. Because real-life anxiety is often temporally diffused. It's not just 1 second of feeling like you're going to fall off a cliff. You feel anxious for a long period of time often. And during that sense of anxiety, most people have to be engaged in goal-directed behaviors. They have to get up and go to work. They have to get up and feed themselves, etc. So successful execution of any goal-directed behavior requires, this is something cognitive neuroscientists have known, that requires proper coding and temporal organization of multiple events. And I'm just listing a few examples of these events: cue processing, memory recall, action planning, reward outcome, expectation processing, etc. That each of these are regulated by different networks in the brain. And so the question that we still have, that we beginning to try and address, is which of these behavioral events are computed differently under a fog of anxiety. I'm sorry, there's a typo here. It should be a fog of anxiety. Okay. That's what you get for having foreigners give you talks. Find typos in their talks. Anyway, so the question we have is which of these behavioral events are computed differently under a fog of anxiety. Now, I'm going to tell you about 3 questions that we have been asking. One, of course, is how to model a fog of anxiety while an animal is engaged in goal-directed behavior. That's not a trivial question. And we are also interested in understanding what brain regions and circuits to record and manipulate once we have this behavior design. And last but not least, we're really also interested in how anxiety is learned by these circuits, because as I will briefly mention at the end of the talk, many forms of anxiety could be actually learned. So let's talk about how to model the fog of anxiety while an animal is engaged in goal-directed behavior. This is not a trivial question. A perfect model, and there's no such thing as a perfect model, is that you have an animal that's happy in its home cage, you train it to do a goal-directed task, and then magically we introduce a fog of anxiety. So the first set of experiments that we did, we took the easy way out, and that was actually a smart thing to do at the time, because it started giving us clues about how different brain regions that we were interested in could be reacting to this. So by easy way out, I mean that we actually used a pharmacological approach. So instead of, so we induced the fog of anxiety by giving animals that are fully trained to do a task an anxiogenic drug. So anxiogenic drugs are very similar to anxiolytic drugs like Valium and Xanax, except that they do the opposite. They still act on the chloride channel, but instead of enhancing chloride flow, they actually reduce it. So they produce transient anxiety, and it's a model that has been around since the 60s. And these drugs can produce anxiety in human, monkeys, and rodents. So using this, I'm going to tell you what, based on this study, which we did several years ago, we started getting clues about what brain region we should potentially be focusing on. So let me tell a bit about that. I'll come up with the conclusions of what that study showed us, then go back and then tell you about actual behavioral models of causing that fog of anxiety. So we started with 2 regions, dorsal medial prefrontal cortex and the Vta. Prefrontal cortical neurons are so-called doer neurons. They're involved in action selection, but they also encode internalized information at the service of distant future actions. So if you're anxious, but you need to do a goal-directed behavior, prefrontal cortex reason must be involved to actually plan for that. And dopamine neurons in the Vta are also involved in encoding both reward and temporal uncertainties. And the working hypothesis we had was that coordinated activity between prefrontal cortex and the Vta is involved in computing behavioral events that are affected by anxiety. In this case, by a drug that causes anxiety. So for these studies, we recorded spike activity and LFTs. And for more recent studies, we also have applied pyrophotometry, and I'll tell you why. I'd much prefer to actually record from neurons than the pyrophotometry. I'll tell you later why we actually switched for some of the studies. But let me very briefly just show you the conclusions of what this pharmacological study was. So we trained the rats to do an extra-dimensional step-shifting task. This is a highly cognitive task, which animals are encouraged or learn to switch from a light rule to a side rule to get a reward. And we gave animals the anxiogenic drug FG7145 as they were doing this task. And essentially the conclusions was that anxiety evoked hypofrontality, so reduced activation of prefrontal cortex and disruption of rule-relevant encoding in the prefrontal cortex, but only during action encoding, which was really interesting. I'm only showing the title of this paper because it was published 4 or 5 years ago. It's a very analysis-heavy paper for those of you who are interested in learning more about this. But I'm going to move on because this paper obviously only was looking at the effect of a drug. So we weren't sure whether it's like actually the effect of anxiety or some indirect drug effect that is causing us this specific action encoding in prefrontal cortex during specific disruption and action encoding. So let me then summarize what we learned from this paper, which was that the same goal-directed action is encoded differently by prefrontal cortex neurons under a pharmacological model of anxiety, and that oddly, action encoding may be a vulnerable locus in networks associated with anxiety. And oddly, because I did not expect this, I assumed that if brain is dealing with anxiety, it's mostly potentially cue encoding or reward encoding is affected. So this was interesting, but it actually proposed more questions than answered any in terms of how your brain is dealing with anxiety. So now let me go back to our first question, which is how to model a fog of anxiety. We have been thinking a lot about how to actually design a model to do this, a behavioral model to do this. And what I'm going to do is to take the rest of the talk today to tell you about 2 behavioral models that we have had that hopefully are producing anxiety, tell you a little bit about the design of the behaviors, and then also show you each behavior, show you a data slide with the behavior, show you that anti-anxiety drugs, Valium, actually does change behavior, so suggesting that these are good models of anxiety, and also give you some examples of how the brain is actually encoding behavioral events when we introduce the so-called fog of anxiety. So how did we go about modeling these behaviors? We started by appreciating that anxiety and fear are related, but anxiety and fear are different. They're not the same thing. Fear relates to a concrete event that is occurring or is certain to occur. Anxiety, on the other hand, is often evoked when potential harm may occur, but the probability of its occurrence is low or uncertain. So let me give you an example. Let's say you're hiking with me in southern Colorado, and this guy jumps at you. That is fear. That has nothing to do with anxiety. You are just really scared feeling fearful if this happens. But as you're walking, if there's no mountain lion, and you know that there are mountain lions around, your brain knows that there's low probability of mountain lion. And that may make you anxious, but regardless, the majority of you, if you do like to hike or exercise, you prefer to hike there versus here, where there's a zero probability of a mountain lion. So, but let's say that you are hiking and then you get to the end of the trail, you pull out your phone and there's a text from a friend asking you if you're hiking, you say, yep, and then the friend responds, be careful, Bob saw a cat near 4 Mile Falls yesterday, and 4 Mile Falls is where you're hiking. At that point then, your brain most likely is going to go from not worrying about it, which is zero, or worrying a little bit about it, low, potentially calculating high probability of mountain lion attack. So most of you will not freeze and scream. You'll come back and hike back, but your behavior may change. You may be walking slower or faster. But regardless, we were interested in modeling something like this and just seeing how the same actions, which is like getting to the end of the trail, are encoded differently if your brain is calculating high or low probability of something bad happening. With that in mind, we started defining some forms of anxiety as a function of harm probability, with the idea being that actions executed toward obtaining a reward are often associated, and this goes for any action, not essentially, the probability of harm occurring during action execution. And learning this probability allows for appropriate computation of future harm to guide actions. So with this definition in mind, which could apply for some forms of anxiety, not all, of course, let me then tell you about our tasks. So task one, we started simple. We have a cue, then animal has to execute an action after that to get an outcome. This is just a fixed ratio 1 FR1 task. But we then introduce variable harm probability during action execution. So this is a version of probabilistic punishment task. And the way we run it in different ways, but the way I'm going to first ran it, I'm going to show you some electrophysiology data and behavior is this way. So we had risk of shock being 0, 0.06, and 0.1. So essentially, this is how the task was run. So you had 3 blocks here. I'm going to show you some data with this response time here. This is when animals expect that they could be shocked here. And then response time after reward delivery and consumption, which tells you if the animal is motivated despite being anxious to receive the reward. So as the shock probability increases, if this response time increases, consistent with the animal being anxious, and so does the probability of response time. Again, this is also consistent with human models of anxiety, but the response time to retrieve reward does not change. The animals are remaining highly motivated to get that reward. Now let's look at the effect of Benzodiazepine, Diazepam, which is an anti-anxiety medication, and that's shown here. So we ran it in like 3 consecutive days where animals received saline one day, diazepam, and then saline again the 3rd day. And as you can see, diazepam essentially reverses that increase in reaction time, suggesting that this is that slow reaction time is a good measure of is reflective of animal being anxious. So task 2. The task 2 is very similar to task 1, except that we introduce another action there as a control. And when you do electrophysiology, it's always good to have with a lot of controls. So here, the animal has to execute an action during which it can get shocked, and the probability of the shock changes. After that, the animal has to do another action. It's a no spot. So these two are very much identical mechanically, except that the seek one is associated with the shock, the take one is a safe action. So this gives us a good way to control for the actual motoric impact of the task. And after that take action, the animal can get a reward. We also have been running this task differently in that we can, and again, this could apply to either task, we continuously increase the harm probability. And this is also a really good model to also see if we have highly impulsive animals that really don't care how badly, what the probability of shock is, and they can stick with the with the task. I do have a video that wasn't loading that well, so I'm going to pass on that with apologies. The paper was published a couple of years ago, and a year and a half ago actually, and it does have some video files if you would like to look at it. Okay, so let's show you the behavior. So this here I'm showing you here is trials completed as we increase the probability of shock. This is session 1 to day 1. The animals are getting it for the first time. I'm showing you this because, as you see, as the animals learn the task, the response becomes highly stable. So if you actually look at the response on day 1, is different than after day 4. The performance become very stable, which makes then also very good for recording or any manipulation, the circuit manipulation studies. So another behavior I'm going to show you is the response time. We seek, take, and reward. So response time decreases as shock probability increases, very much like the other task. Whereas the take one, which is a safe action, the response time stays relatively stable and super stable when the animal just has to go and grab and reward. And similar to the other task, Diazepam also influences this response time here. So this is and trials completed. So both trials completed and latency to response during the risky trials, the effect is diminished, that slowness is diminished in the presence of a low dose of Diazepam. So now let me just show you examples of recordings that are using either of these tasks that are starting to give us clues about how the brain is encoding risk of harm. Again, remember that in these tasks, first the operand making them highly applicable for electrophysiological recordings, for unit, LFTs, and also pyrotechnometry. But what is important to appreciate also is that the animal's behavior is changing even though the actual events are not. So going back to the task, the animals still get the same cue regardless of the harm probability, have to execute the same action and obtain the same reward, which is really nice because you can follow the same cells, the same units in a given recording session as the harm probability changes to see if there's an effect on processing when the only thing that's being changed is the probability of something bad happening during action execution. So for this task, we're recording from Vta and Prefrontal Cortex. Let me show you the data, just some plot raw data for block 1, and this is when there's no risk of harm. So this is, again, the heat plot. These are medial prefrontal cortex unit, Vta, dopamine and non-dopamine units. And this being a heat plot, as the colors get warmer, the cells are firing faster. So this is very classic response. We have Vta neurons showing phasic excitatory response in all tasks, especially reward. Whereas prefrontal neurons, prefrontal cortex neurons are having a very mixed and different set of responses. Again, this is very classic prefrontal cortex. So you have some cue responsive, some action, and then you have the classic, and I'll come back to this, this is really important, this is the classic inhibitory response during action execution that you see when rodents are doing goal-directed actions. So that's, again, this is, I showed you data from block 1. Let's see, then what we did was we followed the same cells and see if any of them changed their tuning properties if we changed as animals going through block 2 and 3. And in fact, we did see some good number of cells that did this. This is some good examples of Vta prefrontal cells. Again, the same cell going from block 1, 2, and 3 during action and reward encoding. So not all the cells change their tuning properties, but substantial portion of them did. So if you look at all of the data, prefrontal, dopamine, and non-dopamine Vta cells, this is the percent of risk encoding units, and these are the units that changed their properties significantly when you went from block 1 to 2 to 3. And interestingly, with this model as well, the most salient or the largest change in firing properties was during action encoding. So similar to the pharmacological model, it seems that here also action encoding is responsive to this model of anxiety. I'm also going to show you one LFP units. If there are any people in the audience who like LFPs, we always record at least LFPs from at least one electrode in our setup because of its relevance to human studies and its and to human EEG studies. So with LFPs, what we noticed is that there's in both Vta and prefrontal cortex, there's this 8 Hz oscillation during task performance, mostly that starts during cue and goes through action execution. And what's really interesting is that this happens when there's no risk, but this 8 Hz activity very much declines, essentially dissipates when animals enter the shock or the punishment risk route. That was an example. This is all of the data. Again, the 8 Hz power is diminished as animals go from block 1 to 2 to 3 in Vta and prefrontal cortex. And what also changes is, of course, the coherence between Vta and prefrontal cortex. So this is was a very dynamic shift in how these regions are interacting. This paper was also published a couple of years, 4 years ago, and there's also another analysis-heavy paper. If you want to check it out, we looked at a number of ways to see what region is driving what, because these recordings were simultaneous. And the analysis that we did, and I'm showing it an example of a time-like phase locking analysis, they all reveal that entrainment of prefrontal neurons is by Vta. So it's all the directionality was always Vta to prefrontal cortex. So what is going on is that as the risk of punishment increases, this Vta control of prefrontal activity seems to be weakening or diminished. So recordings from these data okay, so let's go back to summary 1 with the pharmacological study, which I had told you that you started wondering whether action encoding is a vulnerable locus in networks associated with anxiety. So with this task, the task 1, the recording actually also showed that in fact, coded different prefrontal cortex and Vta dopamine neurons, and that action encoding remains a vulnerable locus. So I think by now we were pretty convinced that in fact it is action encoding that's most vulnerable when the brain is dealing with potential fear that something harmful may happen in the future. And our data also showed that bingo-directed actions are anxiety-free. Vta dopamine neurons drive oscillatory activity in the prefrontal cortex, but as anxiety increases, strength of this synchronous relationship decreases. And the working model that we have that is beginning to be tested is that, so during anxiety-free setting, the Vta neurons are initially driving some activity in the prefrontal cortex that then essentially collapses. So both unit and LFP, so at multiple time scales, the Vta and prefrontal cortex are interacting, and that punishment risk as a model of anxiety diminishes this level of interaction. So it's essentially there's this functional bottom-up disconnection of dopamine cells from prefrontal cortical activity. And this is very much during action encoding. So this, you would argue, could be a bad thing, but I would say that this is anxiety, normal anxiety is a normal thing, and it's important for prefrontal cortex to be flexible to potentially find a way out of a potential harmful situation. So I would argue that this may be a good thing because bottom-up regulations are very strong. So if prefrontal cortex can actually free itself of VTA control, it could then potentially gain more control over planning actions in the face of adversity events. So this is a question that could potentially be tested with more recordings and manipulations of the task. So I'm going to, in the interest of time, I'm going to shift the second task. Remember the one that had the seek and the take version, and tell you about another way of thinking about anxiety, which is how is it learned. So I showed you the lion example that could elicit fear and anxiety if you think there's a probability of mountain lion attack. But you could argue that we are fearful of predators like this guy because you're hardwired. You didn't have to learn to be fearful of him. But we're fearful of this because we have learned to be fearful of this. And going back to the model that we really started all of this experimental design, it's really so much about learning the probability, because harm probabilities are learned. There's learning this harm probability that allows us not only to be anxious, but to compute future, to compute our future actions to help us with action selection. So with the second task, I also showed you this data, which is it shows you that the animals actually are learning, in that behavior in session 1 is different than sessions 4 to 6. So this is a really nice behavioral measure because it will allow us to compare encoding of different events on day 1 versus when the animal has learned the task on day 4, after day 4, to see what brain regions are involved in learning, or what events are involved in learning, to learning of harm probability. So for this task, though, I'm going to switch to fiber photometry because one of the things I didn't show you for the previous task was the impact of shock. Because if you're doing recording from units, there's noise interference, so you cannot actually record while the animal is receiving the shock. With fiber photometry, however, it's easy to do that. So what it allows us to do is to compare punished trials versus unpunished trials. Now, why is that important? It's important because the animals could be changing their behavior because the shock perception could have changed. They could have become sensitized or desensitized to the pain of shock, or the aversion of shock, as opposed to calculating the probability that something may happen. So for the seek trials, I'm going to show you what happens during trials where the animals actually got shocked versus the trials where animals did not get shocked, but they thought that they did. So if you look at session 1, when the animals were shocked, and as we are ramping up the harm probability, it's a profoundly large activation in the prefrontal cortex. And for the interest of time, I'm only focusing on prefrontal cortex. Similar massive effect also exists in the VTA. But what's really interesting is that after the animals learned that basic response did not change in the prefrontal. So clearly, even though the animals had learned the task, prefrontal cortex encoding of the shock perception had not changed. And then let's now look at the encoding of seek actions when the animals are not receiving the shock. This is our control studies when trials where animals did not receive the shock. We see a reduction in neural activity in session 1 during action execution here, which this now changes in that this reduction actually decreases after learning. So prefrontal cortex encoding of action, which is an inhibitory response, is diminished after the animals learn. So what does this mean? We actually think that this global calcium change after fiber photometry actually represents single unit encoding, because if I remember, I showed you the raw data for the during the other task where the animal is not getting a shock and there's this inhibitory response, which if you look at that task as the probability of shock increases, then that inhibitory effect also reduces. So there is a correlation between unit activity and fiber photography. So the safe take, however, doesn't change. So remember that this action and this action are very much the same motor behavior, except that this one is associated with a risk of harm, this one is safe, and that doesn't change with learning. And I should also say neither does reward encoding. So with this task, now I think that we have several behavioral models to measure learning of harm probability associated with reward-guided actions as a potential model of anxiety, and that medial prefrontal cortex adapts its responses selectively during risky actions as contingencies are learned. So this is really interesting and exciting because by being able to measure learning, it really provides us ways of looking at how the brain potentially learns to be anxious. And we are definitely extending our mechanistic studies beyond the prefrontal cortex. So let me then end by talking about ongoing work. So we are doing recordings from multiple regions other than the prefrontal cortex, including other cortical regions such as orbitofrontal cortex. We are looking at both micro and macro circuitry of prefrontal cortex during and after learning. We're also looking at some pharmacological responses because this behavioral task and the recordings could potentially provide a good behavioral model to look and see if they're better anti-anxiety meds than diazepam, Xanax-like compounds. So I'm going to just show you one slide related to just the circuitry work that we're starting to do, and one slide related to impact of psilocybin as a psychedelic. So with micro and macro circuitry, a dumbed-down version of the circuitry that you're interested in, of course, are the prefrontal principal cells that go down to the Vta, and then the dopamine that comes up to the prefrontal cortex, and of course the inhibitory neurons that are in the prefrontal cortex. Given that we had seen an inhibitory response being highly responsive to learning of shock probability, we are thinking that this inhibitory response attenuation could be due to an increase in interneuron signaling or changes in the monoaminergic, potentially dopaminergic or noradrenergic input to the prefrontal cortex. So we're starting with manipulating the prefrontal cortical GABA neurons by optogenetic manipulations. And the nice thing about applying optogenetics to this task is that you can actually modulate GABAergic activity during different behavioral events. And so far, the very preliminary data that we have suggests that in a limited number of animals, that manipulation of GABA interneurons could in fact shift the learning curve, in that in session 1, animals before they learn GABAergic inhibition is very much shifting them to well-learned animals. And then with pharmacology and psychedelics, we were interested in seeing if a drug like psilocybin affects learning of this task, or after learning affects performance. So again, remember that we had a nice learning curve, that performance on day 1 and later sessions was different. So we designed the experiments this way by just giving animals psilocybin on day 1 when they were trying to learn the task, and also after learning. Well, psilocybin has absolutely no effect on learning on this task or other tasks, but after learning, the effect is interesting in that, again, this is preliminary data, so this is actually only 5 animals with a low dose of, maybe 6 animals low dose of psilocybin versus control, and by the time you get to 3 mg per kg, they're pretty much knocked out, so they're not performing the task. I'm just showing you 2 of those animals, but regardless, with a lower dose, what you see is this shift in trial completion, in that they seem to care less about being shocked up to a point. And it's good that it's up to a point, so it's not just that they become very impulsive, but that they seem to be putting up with the harm probability slightly longer than control animals. And what's also interesting about this is that another so-called psychedelic, which is not a positive drug, it's actually, because it's profoundly anxiogenic, causing anxiety, DOI, That drug does the expected effect of shifting the curve to the left because it's making the animals more anxious from the onset and before we start applying additional treatment. So this suggests that this is psilocybin is having an interesting effect potentially on some aspects of this test. But again, this is preliminary, so we will know. You'll see how this effect lasts, and also what is the effect on neural encoding of events when animals are performing the task. So to conclude, I hope I have convinced you that the same goal-directed and reward-guided action is encoded differently by prefrontal cortex and Vta neurons under anxiety, and that action encoding is a vulnerable event in networks that are associated with anxiety, and also that learning of harm probability is an important construct to study because it may provide a novel approach to study the etiology of some forms of anxiety. So I'm going to end by showing you the picture of current folks in the lab. We had an unusually nice sunny day in Portland, so we were outside in our Hawaiian shirt. These are list of present and relatively recent lab members. Current members are depicted in blue. Those who contribute to the study are depicted in gold. Grateful to my funders as well as some collaborators. And also then I will end because I mentioned ALBA as something I would like to promote. It's a wonderful organization. Please go look them up. And we just started by a number of scientists, mostly women scientists, diverse group of women scientists internationally. Check out their mission and why, what is it that we do, and if you can be involved and contribute to the cause, please do. So with that, I thank you for your attention and happy to answer any questions if there's time, and if that's what we do in this, I wasn't sure. Anyway, thank you so much.
Thank you so much, Vita. So we have about 10 minutes or so for questions. We have one in the chat, so if you have a question, just type it in the chat. The first one comes from Victoria Corbett. She writes, "Hi Vita, great talk and really cool behavioral paradigms. Can you clarify for task 1? So I believe that's the variable harm task. I thought you showed that the behavioral differences with the risk probability were largely in the reaction time after the cue, when the shock could happen. But then in the electrophysiology data, you highlighted the peri-action time as showing the biggest change with risk probability. Is the highlighted effect in the electrophysiological data coming from the same time period when the behavioral difference occurred?"
So that's a great question, and one that we really can starting to answer because in order to compare, we need probably better measure of behavior as opposed to just action executed. So all we were measuring in the behavior data that I showed you was action executed or the time that it took from the cue till action execution. And now that we started analyzing the behavior with the gap approach, and then we can potentially do a better correlation of what the animal was doing during that delay period and correlate it with the peri-action activity. So good question. You don't have the data to answer it now, but the reaction time, yeah. So that's essentially what I can do at this.
Okay, cool. Another question comes from Kelly Kennebrew. Thank you, Vita, for this excellent work. Your ongoing psilocybin research is particularly fascinating to me. Should we go to the site to follow and get involved if it makes sense?
Site for ALBA, yes. Is that what?
I guess your lab site for the psilocybin.
Psilocybin is just starting. Nothing is published. We have psilocybin involved in another project that I didn't mention, and that behavior for that data is we're writing that up. As soon as you write it up, you're putting everything on bioarchives now, so it will be there and it will be in a lab's archive, yes. But right now you won't find anything on psilocybin lab website because we're not posting anything to preliminary, and what I showed you is of course very preliminary, it's only a few animals. Yeah, so, but the other study, which is looking at the impact of psilocybin on a behavioral flexibility tasks, very similar to the task that I showed you with the drug, anxiogenic drug, that's that shifting task in the Journal of Neuroscience paper 4 years ago. That task, we have looked at the effect of psilocybin and we've seen some interesting effects. So that behavior data is being written up, and as soon as it is, will be in the bioarchive.
Okay, cool. I had a question about the psilocybin work. Are you framing the psilocybin work as potentially, a way to unlearn some of the anxiety, learned behaviors? Because you mentioned how the circuits might be able to learn it, and then for therapy, of course, we think about unlearning circuits and perhaps what might be the mechanisms for this.
To be honest, I'm not framing it in any way because we have no idea how it works. The effect it has, so the reason I showed the DOI data is that DOI is a very selective 5-HT2A targeting drug. So if the effect was through the receptor that everybody thinks psilocybin is acting, DOI should act the same, but it's not. The impact it has in human behavior in terms of the ability to respond better to psychotherapy is really interesting. It would be very difficult to model it in animals to come up with a really clear mechanistic way that it is doing. I mean, there are a lot of really nice work out there, a lot of interesting ideas. But I am completely going into this work with an open mind and not and very, very hypothesis question free because it's a very interesting drug. We really don't know how it works.
Cool. I have one final question, and this is a much more specific question from your talk. I am someone who works on EEG, so I was very interested in the LFP data. And you showed synchronization between Vta and medial prefrontal cortex, and you showed, it appeared to be very specific to the alpha and perhaps low beta frequencies. And those rhythms, of course, these are, there are a lot of mechanisms for them between the thalamus as well, specifically the medial dorsal thalamus. And do you think the medial dorsal thalamus might play a role in some of these behaviors and perhaps, coordinating the cognition related to anxiety?
I think it must. I mean, I think that would be one of the candidate regions that could potentially influence in a very dynamic way because really something else is coming in and manipulating the activity as well in a very dynamic way, only when the risk probability computation is shifting. So thalamus, yes, and because it also heavily projects, especially to prefrontal cortex, so it could have that sort of an influence on it. Yes.
Cool. Awesome. So I think those are all the questions that we had. Again, there will be a Q&A to follow right after this, or right now. So to everyone, we can migrate from this Zoom to the Q&A link, which is in the chat. And again, I'd like to thank Vita for this amazing talk. Talking so much.
Thank you. Okay, so I should do the other one as well.
Yes. And so I will see you.
Recording stopped.
I will see you at the other Zoom.
Let's see. Okay, and was that other one was sent to you, right?
Yes, and I